Morning everyone. Myself is Chaitra, lecturer of Physics, Department of Physics, IDSG Government College, Chikamagaluru. So today class I am going to discuss about the first BSc second semester physics practicals paper 2 experiments. So before we are discussing the practicals, firstly we should know about the list of experiments which are under second semester BSc students. Here is the list of experiment list. So that is there are 8 experiments which are conducting for a second semester BSc students. Among the 8 experiments, now let us see one by one. First one is frequency of AC by using sonometer, and the second one is Stefans Boltzmann fourth power law. Third one is verification of parallel axis theorem, and the fourth one is surface tension by droplet method. The fifth one is Helmholtz resonator. Sixth one is Young's modulus, that is small q. You have already discussed in the elasticity chapter last semester. So that you are going to calculating your Young's modulus q by single cantilever. So and the torsional pendulum, and the eighth one and the last one is Young's modulus small q by Koenig's method. These are all the 8 experiments we are conducting for a second semester students. So next we will discuss one by one in detail with the experimental setup. So among that one, firstly I would like to take Stefans Boltzmann's fourth power law, that is verification of Stefans Boltzmann fourth power law. So now let us discuss in detail of this experiment. Stefans Boltzmann fourth power law. The aim of the experiment is to determine, or here to verify, not to determine, here to verify the Stefans Boltzmann fourth power law by using an electrical circuit. Here we are going to use the electrical circuit. By using this electrical circuit, we are going to verify the Stefans Boltzmann fourth power law. For that, so in this experiment, so in order to verify the experiment, we need an apparatus. So they are meter bridge. We need an operator setup, that is meter bridge, battery, resistance box, rheostat, pointer, and the galvanometer, a small milliammeter with the filament lamp and the plug key. These are the operators we need to do the experiment in order to verify the Stefans law, right. So in next I will show you in detail operator setup. So before that one, now again let us know the formula we are going to calculate the resistance. So formula under, that is in order to find out the radiation index, a small formula. So before radiation index, firstly we should calculate the resistance of the bulb in every case, in every trials. Okay, so a small formula is required. That formula is capital R is equals to S into L divided by 100 minus L in terms of ohms. As you can see, that is SL divided by 100 minus L in terms of ohms, where R is called as resistance of a bulb and S is called as standard resistance, where L is called balancing length. Here there are two formulas we are going to use. One is to find out the resistance and another one is radiation index. And radiation index can be calculated by using, you are getting the slope of log p versus log r. If we plot a log p versus log r graph, we will get a straight line. By using that straight line, find out the slope. So that slope will give you the radiation index value. Okay, so where P is nothing but a power radiated by the bulb, and the power P can be calculated by using the formula, so that is I square into R. Okay, so you are already familiar with this in your basic studies, that is P is equals to power R I square into R, where I is equals to current in the circuit, where R is called as resistance of the bulb, right. So next we'll see the circuital arrangement in order to verify the Stefans law. So this is the circuital arrangement, as you can see. Okay, so according to Stephen's law, so you are already familiar with this in your in second semester students, you are already learned the Stephen's law in radiation chapter. Okay, in radiation chapter, so what is the statement of Stephen's law? What he told that? So that statement is, it states that the total energy radiated per unit surface area of a black body in unit time, that is per unit time, is directly proportional to its fourth power of its absolute temperature. That is, the total energy radiated per unit surface is directly proportional to fourth power of its absolute temperature. That is, the radiation is nothing but the emissivity, that emissivity or also emissivity is directly proportional to fourth power of its absolute temperature. So emissivity is represented by the symbol sigma. So that is, you are already discussing in the radiation chapter. Okay, so now let us see the circuital arrangement in order to verify the Stephen's law. This is about the circuital arrangement, where it consisting of a meter bridge of two arms, that is A, B, C, D. As you can see in the figure, you can see the arms A, B, C and D, right. So this meter bridge consisting of two arms, and this meter bridge is connected to the battery of old power supply, that is power supply is connected to the meter bridge with the plug key, in series with the plug key. Next, the plug key is connecting in series with the rheostat. So this rheostat, upper end of the rheostat is connecting to the another end of the meter bridge, and lower end of the rheostat is connecting to the plug key as shown in figure, right. So again you will see the and upper arms in the meter bridge, and among that one, first upper arm is connecting to the glowing bulb, as you can see the glowing bulb. So this glowing bulb is connecting in series with the milliamps. So see that small m, capital A is nothing but a milliammeter. A small milliammeter is going to use. Next, so this will connecting to the where C is called as balancing point, found using the sliding contact. So C is nothing but C ಗೆ ಏನಂತ ಕರೀತಾರೆ, balancing point, find out using the sliding contact. And another arm of the meter bridge is connecting to the S. S is nothing but a resistance box, varying resistance box. Here we are going to unplug the corresponding. So ನಮಗೆ ಯಾವುದು resistance ಬೇಕೋ, a suitable resistance is unplugged by using the resistance box that is connected to the meter bridge. Okay. In middle the point C is balancing point. At that balancing point a small galvanometer is arranged. See the galvanometer is connected, so that one end is remains fixed and another one is sliding over the meter bridge. Okay, so one end is remains fixed and another one end is sliding over the meter bridge. So this is nothing but a circuital arrangement. So the symbolic representation is also written like this. Small ma is nothing but a milliammeter resistance box, G is nothing but a galvanometer, C is balancing point found out using the sliding, and battery with the plug key with the rheostat. Okay, this is the circuital arrangement. Next we will see the functioning of the circuit, how it is going to functioning. Initially a suitable resistance, so initially a suitable resistance, that is S, capital S, as you can see S is known. So in that S you are going to unplug the suitable resistance, almost say for example sometimes 5 ohm, 6 ohm, okay, depending upon the glowing of the bulb. So here we are putting unplug 5 ohm. Okay, so we are taking we are unplug 5 ohm of resistance in a resistance box, then vary the rheostat. Okay, so we are going to vary the rheostat value. So when varying the rheostat value gradually such that the bulb begins to starts to glow, you can see the bulb, right. So when the rheostat, you are going to vary the rheostat such that the bulb begins to glow. Here you can see the bulb, bulb begins to glow. So when the bulb started to glow, then you can note down the current value in milliammeter. You can note down the current, corresponding current in the milliammeter. That will record, that will give you the current, that is capital I. Okay, that will give you the current in the circuit, capital I in milliammeter. Okay, so soon after that one, move the sliding contact, that is galvanometer sliding contact, as you can see point C and point D. Okay, so one end is remains fixed and another one end is remains sliding over the meter bridge, right. So that sliding will move, when move the sliding contact at the meter bridge. Okay, from A to B, as you can see from A to B you can slide the pointer, then when you are going to sliding the contact, the galvanometer pointer, in galvanometer pointer which shows the zero deflection. Okay, so when it gives you the zero deflection, when the galvanometer pointer shows the zero deflection, that point is called as balancing point, that is noted in capital D. So capital D refer ಮಾಡಿದಾರಲ್ಲ ನೋಡಿ ಅಲ್ಲಿ, so that is nothing but a balancing point. So ಒಂದು ಪಾಯಿಂಟಿಗೆ ಏನಂತ ಕರೀತಾರೆ, when the galvanometer deflection shows 0. Okay, so that point is called as a balancing point. From A to D, that corresponding length is called as balancing length. Okay, you have to note down the balancing length and you just note down in the balancing length column, tabular column, as we have the tabular column in, so below that one you can see first one is current in the circuit, that is first you note down the current in the circuit in terms of a milliamps, then you should note down the balancing length when the galvanometer deflections 0, which shows the 0 deflection. Okay, that is current in milliamps and corresponding length is balancing length. Next you are going to find out the corresponding resistance value, capital R, that I have already told, that is R is equals to SL divided by 100 minus L, where S is nothing but a resistance, a suitable resistance unplugged in the resistance box, and L is nothing but a balancing length. By using this you are going to calculate the resistance value, then plot a log or and also calculate the resistance value log for the resistance value. ಓಕೆ, ಸೊ ನಿಮ್ಮ ಕ್ಯಾಲ್ಕುಲೇಟ್ರಲ್ಲಿ ಆರ್ ರೆಸಿಸ್ಟೆನ್ಸಿಗೆ ಏನಿರುತ್ತೆ ಅದಕ್ಕೆ ಆರ್ ವ್ಯಾಲ್ಯೂಗೆ ಲಾಗ್ ತೆಗೀರಿ. ಯು ಕ್ಯಾನ್ ಗೆಟ್ ದ ಲಾಗ್ ಆರ್ ವ್ಯಾಲ್ಯೂ ಫಾರ್ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಲಾಗ್ ಆರ್ ವ್ಯಾಲ್ಯೂ. ನೆಕ್ಸ್ಟ್ ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಪವರ್. ಓಕೆ, ಸೊ ಪವರ್ ಹೇಗೆ ಫೈಂಡ್ ಔಟ್ ಮಾಡ್ತೀರಾ? ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಫೈಂಡ್ ಔಟ್ ದ ಪವರ್ by using I square into R formula. Okay, so I square is nothing but a current flows in the circuit. We have already noted out. Okay, so that current into resistance, you will get the power. Okay, corresponding next end ಮಾಡ್ತೀರಾ. So you are going to taking the log of the power value. This is how the tabular column, how you are going to calculate the tabular column. So that is current in the circuit, balancing length, resistance, log R value and power. By using power you are going to take the log P value. Okay, this is first one. In the next one what you have to do? Repeat the same procedure. Okay, repeat the same procedure by increasing the current. Okay, so how? So you are going to increase current ನ increase ಮಾಡಬೇಕು. How you are going to increase? By varying the rheostat value. Okay, so by varying the rheostat value you are going to see, you are going to vary the current value. So when you are going to vary the rheostat value, so the corresponding variation of current is showing in the milliammeter. ನೀವು ಯಾವಾಗ rheostat vary ಮಾಡ್ತೀರಾ that corresponding current milliammeter ಅಲ್ಲಿ ತೋರಿಸುತ್ತೆ. So how much you are going to vary is nothing but, so say for example ನಿಮ್ಮದು ಫಸ್ಟ್ ವ್ಯಾಲ್ಯೂ ಒಂದು 80 ಮಿಲಿ ಆ್ಯಮ್ಸ್ ಬಂದಿದೆ ಅಂತ ಹೇಳಿದರೆ ನೆಕ್ಸ್ಟ್ ಟ್ರಯಲಿಗೆ ಏನು ಮಾಡಿ ಅಂತ ಹೇಳಿದರೆ 90 ಮಿಲಿ ಆ್ಯಮ್ಸಿಗೆ 90 ಆ್ಯಮ್ಸಿಗೆ ಬರೋ ಥರ ಸೆಟ್ ಮಾಡ್ಕೊಳ್ಳಿ ಬೈ ಯೂಸಿಂಗ್ ರಿಯೋಸ್ಟ್ಯಾಟ್. ಓಕೆ, ಸೊ ಬೈ ಯೂಸಿಂಗ್ ರಿಯೋಸ್ಟ್ಯಾಟು ನೀವು 90 ಮಿಲಿ ಆ್ಯಮ್ಸಲ್ಲಿ ಕರೆಂಟನ್ನು ನೋಡ್ತಾ ಸೆಟ್ ಮಾಡಿ. ಸೊ ನೆಕ್ಸ್ಟ್ ಅಗೇನ್ ಏನು ಮಾಡ್ತೀರಾ? ಸ್ಲೈಡಿಂಗ್ ಗ್ಯಾಲೋನೋಮೀಟರ್ ಅನದರ್ ಒನ್ ಎಂಡ್ ಏನಿದೆ ಸೊ ಅದನ್ನು ಸ್ಲೈಡ್ ಮಾಡಿ ಯು ವಿಲ್ ಗೆಟ್ ದ ಬ್ಯಾಲೆನ್ಸಿಂಗ್ ಲೆಂತ್. ಸೊ ಗ್ಯಾಲೋನೋಮೀಟರ್ ಡಿಫ್ಲೆಕ್ಷನ್ ಯಾವಾಗ 0 ತೋರಿಸುತ್ತೋ ದಟ್ ಲೆಂತ್ ಈಸ್ ನೋನ್ ಆಸ್ ಬ್ಯಾಲೆನ್ಸಿಂಗ್ ಲೆಂತ್. ಸೊ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಲೆಂತ್ ಬ್ಯಾಲೆನ್ಸಿಂಗ್ ಲೆಂತನ್ನು ನೋಟ್ ಡೌನ್ ಮಾಡಿ. ರಿಪೀಟ್ ದ ಸೇಮ್ ಪ್ರೊಸೀಜರ್. ಫಾರ್ 80 ಮಾಡಿದ್ದೀರಾ, ನೆಕ್ಸ್ಟ್ 90, 100, 110, 120, 30. ಸೊ ಎಲ್ಲಿ ತನಕ ಮಾಡ್ತೀರಾ? ಅಪ್ ಟು ಎಡ್ಜ್. ಸೊ ರಿಯೋಸ್ಟ್ಯಾಟ್ ಎಲ್ಲಿ ತನಕ ಮ್ಯಾಕ್ಸಿಮಮ್ ವೇರಿ ಮಾಡ್ಬೋದು ಸೊ ಅಲ್ಲಿ ತನಕನೂ ಮ್ಯಾಕ್ಸಿಮಮ್ ವೇರಿ ಮಾಡಿ. ಸೊ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಬ್ಯಾಲೆನ್ಸಿಂಗ್ ಲೆಂತನ್ನು ನೋಟ್ ಡೌನ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಸೊ ಈ ನೋಟ್ ಡೌನ್ ಮಾಡ್ಕೊಂಡ್ರೆ ವ್ಯಾಲ್ಯೂಸನ್ನೆಲ್ಲ ಎಲ್ಲಿ ಟ್ಯಾಬ್ಲರ್ ಕಾಲಮಲ್ಲಿ ನೋಟ್ ಡೌನ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಇಲ್ಲಿ ಟ್ಯಾಬ್ಲರ್ ಕಾಲಮ್ ಇದೆಯಲ್ಲ, ಸೊ ಈ ಟ್ಯಾಬ್ಲರ್ ಕಾಲಮಲ್ಲಿ ನೋಟ್ ಡೌನ್ ಮಾಡಿಕೊಂಡು ಫರ್ದರ್ ಎಲ್ಲ ಕ್ಯಾಲ್ಕುಲೇಷನ್ಸ್. ಸೊ ನಾನು ಹೇಳಿದ್ನಲ್ಲ ಹೇಗೆ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಬೇಕು ಅಂತ. ದಿಸ್ ಇಸ್ ಅಬೌಟ್ ದ ಟ್ಯಾಬ್ಲರ್ ಕಾಲಮ್ ಪಾರ್ಟು. ನೆಕ್ಸ್ಟು ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಪಾರ್ಟಲ್ಲಿ ಏನಿರುತ್ತಪ್ಪ ಅಂದರೆ, okay, so in calculation section you are going to calculate. I have already told that R is equals to SL divided by 100 minus L. ನಾನೇನು ಹೇಳಿದೆ? ಫಾರ್ ಇಂಡಿವಿಜುವಲ್ ಟ್ರಯಲ್, ಸೊ ಒಂದೇ ಟ್ರಯಲ್ಗೂ ಕೂಡ ಇಂಡಿವಿಜುವಲ್ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಯು ಮಸ್ಟ್ ಡೂ ಆ್ಯಂಡ್ ಯು ಹ್ಯಾವ್ ಟು ರೈಟ್ ಡೌನ್ ಇನ್ ಯುವರ್ ಬುಕ್ ಆ್ಯಂಡ್ ಆಲ್ಸೋ ವಿತ್ ಯುವರ್ ರೆಕಾರ್ಡ್. ನಿಮ್ಮ ರೆಕಾರ್ಡಿಗೂ ಇಂಡಿವಿಜುವಲ್ ಕ್ಯಾಲ್ಕುಲೇಷನ್ಸ್ ಬರೀಬೇಕು ಆ್ಯಂಡ್ ಆಲ್ಸೋ ನಿಮ್ಮ ಅಬ್ಸರ್ವೇಷನ್ಸಿಗೂ ಕೂಡ ಇಂಡಿವಿಜುವಲ್ ಕ್ಯಾಲ್ಕುಲೇಷನ್ಸ್ನ ಬರೀಬೇಕು. ಓಕೆ, ಸೊ ಆರ್ ನಮಗಿರೋದು ಒಂದೇ ಫಾರ್ಮುಲಾ ಆಗಿರೋದ್ರಿಂದ ಆರ್ ಫಾರ್ಮುಲಾ ರೆಸಿಸ್ಟೆನ್ಸ್ ಫಾರ್ಮುಲಾನ ಸೊ ಪ್ರತಿಯೊಂದು ಟ್ರಯಲಿಗೂ ನೀವು ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಬೇಕು ವಿತ್ ಯೂನಿಟ್ಸ್. ಡೋಂಟ್ ಫರ್ಗೆಟ್ ದ ಯೂನಿಟ್. ಓಕೆ, ದೆನ್ ಸೂನ್ ಆಫ್ಟರ್ ದಟ್ ಒನ್ ಸೊ ಯು ಹ್ಯಾವ್ ಟು ಪ್ಲಾಟ್ ಎ ಗ್ರಾಫ್ ಆಫ್ ಲಾಗ್ ಪಿ ವರ್ಸಸ್ ಲಾಗ್ ಆರ್. ಸೊ ಹೌ ನೋಡಿ, ಇಲ್ಲಿ ಟ್ಯಾಬ್ಲರ್ ಕಾಲಮಲ್ಲಿ ಲಾಸ್ಟಲ್ಲಿ ಪಿ ವ್ಯಾಲ್ಯೂ ಇದೆ, ಇನ್ನೊಂದು ಓಕೆ ಲಾಗ್ ಪಿ ಇದೆ, ಇನ್ನೊಂದು ಆರ್ ಇದೆ. ಸೊ ಲಾಗ್ ಆರ್ ವ್ಯಾಲ್ಯೂ, ಇನ್ನೊಂದು ಲಾಗ್ ಪಿ ವ್ಯಾಲ್ಯೂ. ಸೊ ಇದೆರಡಕ್ಕೂ ಕೂಡ ಅದು ಹೇಗಿದೆ ಯೂನಿಟ್ಸನ್ನು ನೋಡಿಬಿಟ್ಟು ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಪ್ಲಾಟ್ ಎ ಗ್ರಾಫ್. ಸೊ ಗ್ರಾಫನ್ನು ಪ್ಲಾಟ್ ಮಾಡಿ. ಸೊ ಏನು ಮಾಡ್ತೀರಾ? ಲಾಗ್ ಆರ್ ವರ್ಸಸ್ ಲಾಗ್ ಪಿ ಗ್ರಾಫ್ ಪ್ಲಾಟ್ ಮಾಡಿದರೆ ಯು ವಿಲ್ ಗೆಟ್ ಎ ಗ್ರಾಫ್ ಲೈಕ್ ದಿಸ್. ಓಕೆ, ಸೊ ನಿಮಗೆ ಗ್ರಾಫ್ ಈ ಥರ ಬರುತ್ತೆ. ಸೊ ಪುಟ್ ಎ ಗ್ರಾಫ್ ಆಫ್ ಲಾಗ್ ಆರ್ ವರ್ಸಸ್ ಲಾಗ್ ಪಿ. ಸೊ ಯು ವಿಲ್ ಗೆಟ್ ಎ ಒನ್ ಸ್ಟ್ರೈಟ್ ಲೈನ್. ಸೊ ಒಂದು ಸ್ಟ್ರೈಟ್ ಲೈನ್ ಬರುತ್ತೆ. ದೆನ್ ಸೊ ಆ ಸ್ಟ್ರೈಟ್ ಲೈನಿಗೆ ಪುಟ್ ಎ ಸ್ಲೋಪ್. ಸೊ ಒಂದು ಸ್ಲೋಪನ್ನು ಪ್ಲಾಟ್ ಮಾಡಿ. ವಿಲ್ ಗೆಟ್ ಎ ಸ್ಲೋಪ್. ದಟ್ ಸ್ಲೋಪ್ ವಿಲ್ ಗಿವ್ ಯು ದ ರೇಡಿಯೇಷನ್ ಇಂಡೆಕ್ಸ್. ಓಕೆ, ಸೊ ರೇಡಿಯೇಷನ್ ಇಂಡೆಕ್ಸನ್ನು ಕೊಡುತ್ತೆ. ಸೊ ವಿಚ್ ಒನ್? ದಟ್ ಈಸ್ ಸ್ಲೋಪ್. ಇಫ್ ಯು ಪ್ಲಾಟ್ ಎ ಗ್ರಾಫ್ ಆಫ್ ಲಾಗ್ ಪಿ ವರ್ಸಸ್ ಲಾಗ್ ಆರ್ ಯು ವಿಲ್ ಗೆಟ್ ದ ರೇಡಿಯೇಷನ್ ಇಂಡೆಕ್ಸ್. So n, so that is represented by the symbol n. Okay. Okay, so when the straight line will give you the value of radiation index. So when the radiation index is for equal to 4, that is equal to 4. So you can see the value of 4. Your seniors has been done like this. Okay, so when the radiation index value will be found 4, then and hence Stephen's law is verified. So you can write the result. So the radiation index is found to be n is equals to 4. So this, therefore, which is nearly equal to 4, the Stephen's law, Stephen's fourth power law is verified. This is how you are going to explain, or you are going to do the experiment, that is Stephen's fourth power law, Stephens Boltzmann fourth power law. Okay, I hope you can understand. So this is how the Stephens Boltzmann fourth power law. So in the next session I would like to take another one more experiment. Okay, thank you.